on the next layer. So this is a very, so this is like just one layer neural network. And if you want to build multiple layers, then after this layer, so use the output of X1, you can use it as the input of next layer to get like X2. So in this way, you have a deep workflow. So we call this kind of model deep learning. And now,
so yeah, so far is just a regular deep learning.
Yeah, this is regular. So I just want to show that so you can treat like each layer as two steps. The first step is doing the linear transformation. The second step is doing a non-linear transformation. Yeah, like this sigma is I think people call it activity like a function. Yeah, some link function. Yeah. So even so for one layer, so this nonlinear function is limited to what people set. So people set this function, but after like several layers, so this nonlinear functions can approximate a very complex nonlinear function. Yeah, and the parameter we need to we need to estimate in this framework is all W all W matrix. So this we can call it W1 because this is the W matrix for the first layer, and you can also have this W matrix for the second layer. Okay, so this is the traditional framework of neural network. But you can see that so each time the input is just a vector. But how
I have a question after you apply this activate function, then the dimension P reduce into a single number.
No. So this is just okay. Maybe here. So this function is applied to each element of this vector. So Wx, yeah, is d dimension. Since we transform maybe this p dimension to d dimension. So you can also just keep the p dimension. So it depends on your design. And after that, so for each element, yeah, I think like this for each element. So we gave this sigma transformation.
Okay.
Yeah. So yes. Yeah. So
this function is element based.
Yeah, it's element wise. I just use this notation. Yeah. For simplification. Yeah. So let's say dimension D is still the dimension of what you do after linear transformation. Yeah. So you can just treat it as a one-step nonlinear nonlinear transformation for one layer. And now, so what is the graph of convolutional network? So what is the convolution means? So convolution means that you want to so here in this traditional layer, you can see that so each time we own the input is only the information of this cell itself. So we do not use the information from other cells to help learn the information of these cells. So for example, cells. But we know that so cells can be similar to each other. So for example, by our t-SNE or some PCA, we can get like some cells can group together. So yeah, we can use a method like k nearest neighborhood to find the most similar cells for each cell. So we can construct a graph for all cells. So here, so maybe this is one graph, yeah, of these 5 cells. And when we want to generate maybe the low dimensional representation from the original P features of a cell, I also want to use the information of its neighborhood. Yeah, because they are similar. So that is why so now so that is a graph convolutional network. So when we input so when we input one cells, so uh, we also use the information like of its neighborhood. So for the input X, so we also use a convolutional, it's like use a convolutional way to transform it to maybe average of itself and its neighborhoods. So I think we can, if A is the adjacency matrix, which show the graph structure, and we can use, so this is called the normalized the adjacency matrix. So D is the degree of each. D is a diagonal matrix whose diagonal element is the degree of each cell. So this is a normalized adjacency matrix, and we use a convolutional way. Yeah, we use a convolutional way to transform the original features. Yeah, to I mean to list form. I think list form. If you look at the transformed feature, so it is actually an aggregate of the features of a cell itself and all of its neighborhoods. So it's an aggregate. For example, we take the mean of itself and all its one-step neighborhoods. And you can also use other way to aggregate this and define another kind of this matrix. So here, so a very popular way is directly use this normalized adjacency matrix. So this is what graph convolutional network.
Yeah, I think some of the imputation algorithm like magic is using this.
Yeah. And also you can see that this aggregate is just like a smoothing of graph. So so for each input, we smooth it across the graph. Yes. So each step, so in each layer, we do this kind of things. So we borrow the information from its neighborhood to help like gather the information of itself. Yeah, so this is what the graph convolution network. And the meaning of this convolution is to gather the information of neighborhood. Yeah, this is I think the key point of convolutional. And for the graph attention network, so which Chen introduced last week. So it's a way to help us determines determines the similarity between oneself and its neighborhoods. So in the traditional graph convolutional network, people need to give a way to aggregate all its neighborhoods. So usually we give the same weight to our neighborhoods and make the average of them. But for graph attention network, so he tried to use some parameter and build some model to learn so which cell is more important to the target cell. So you can treat it as so using so now we do not so this one is known in graph convolution network, but now we use another way, maybe to do another way of convolution. But in this convolution, we need to learn which kind of weight we have. So this is the key point of self-attention. So in self-attention, so you can learn that. So maybe from in the output, we find that the importance of this cell A to cell B is 0.6, and the importance of cell C to cell B is 0.4. So they are not the same weight. So, but this weight is not people determined. It is determined by the data, by the neural network model. So, I just presented the key point of graph attention network. So,
Yeah,
for
how
the
can you, yeah, but how can you learn this function if you learn from the data itself?
yeah. So, you can treat this one. He also like build a function for it. For example, so I think this one Chen introduced it last week, but so I will quickly introduce like the step of it. So at the beginning, so you have a vector like xb for this B cell, and you have a vector xa for this A cell. And for B, first you give it a transformation. So I do not know which kind of transformation for it. This is what we want to learn. And for A, we also give a transformation. So this one is also we will going to learn. And then so we calculate the inner product of these two transformed information. So the inner product is a kind of similarity. So the results of this similarity, so we call it maybe the score the attention of B to A. Yeah, you can see that. So this W1 and W2 are two parameter matrix, and by introduce so these two parameter matrix, we design a way to calculate a similarity between XB and XA. And in this way, so maybe this A will be plugged in to here by some way, but not directly plug in. He also used some other technique to plug in it. But this attention score, you can treat it as some kind of similarity between A and B. So as a result, so he just put it as a big log function, and then he can estimate the this correlation. I think this similarity by learn. So what is W1 and W2? And this W1 and W2 are shared for all genes. So not just for A and B. So if we want to find what is the relationship from A to C, so he will still use this W1. Yeah, and W2 to construct an attention score from A to C.
Yeah, I saw the A, B, C are cells, but now
Yeah, three
something
cells.
like you are talking about the genes.
A, B, C are three cells.
Yes, 3 cells. Okay.
Yeah, not genes.
Mhm.
So this is the so this is a graph attention network. So I think all the graph-based neural network is to try to use the similarity between samples, not features. So in our study, the cells are samples. Yeah, but the genes are features. So this is the difference between the graph neural network and the traditional neural network is he introduced the links, the similarity between the samples into the original model. Yeah. So this is the attention network. But so once I think one shortcoming so in this kind of problem is first, so it is the transductive method. That is, if now we have a new sample, so it is hard for us to generate to generate its lower representation. because for a new network, for a new sample, our graph will change. So our graph will change. So all the structure, all the similarity we learn, so will not be the same. So after we introduce a new cell. So that is why we call these two methods transductive method. And now, so what we want to introduce is a inductive method. So in this inductive method, so he only focus on like how many so in last way so in graph convolutional network, so we need to know the original network. So we need to know which one is the neighborhood of a target cell. But in inductive method, he do not care about what is the whole set of its neighborhood. He just want to generate the neighborhood of a cell by some technique like random walk. Yeah, for example, so for one cell, so he just so for each cell, so each time when he want to gather the information, so he used the vector of its cell. So example, so here if we have cell A, so we have the feature vector of cell A. So now he want to find 5 first step neighborhood, like neighborhood of A. So how to how to find 5 even so A do not have 5 first step neighborhood, he can use like the way of random walk to generate 5. For example, so in random walk, so each time he begin from A and randomly select next cell connected to A in this graph. For example, he can sample A to B in first random walk. So in the first random walk, from A he select B. And in the second random walk, he select A to C. Maybe in the third random walk, so he also select A to B. So it's okay. So in this kind of method, he allow to select one neighborhood multiple times. So the key point is he want to like search all the one-step information of a cell. So maybe in the fourth step, he selects B again, and in the fifth random walk, he selects C. And now
I
what
have a
you have,
question here. If you don't give the graph, how the random walk can?
you need to have the graph, but you need to make the whole graph as your input.
Okay, as I unweighted graph.
Yeah. So the whole graph means that when you do the graph convolutional network, so you need to input like all the cells and its its features as the input to learn. But in this framework, so each time you only need to input so XA itself and the features and the node like this you sampled. So this is, I think maybe, I know it is a little difficult to understand because this difference is related to how to implement these two methods. So when you implement the first method, you need to take the whole network and the whole expression, hold the expression level matrix at the input. But for the second method, for the method I'm going to introduce, so each time you only need to input the target cell and the neighborhood we generate from random walk. So in this way, so we can divide the whole sample size to some small bunches, and we can use the parallel way or some other way to achieve fast computing.
Okay, so you make this whole global network make it smaller, so it become a neighbor local module, network module,
Yeah,
which
yeah.
around you target cell A. But you still have to have this network first, then you zoom in into this local network
you
to
are
perform
right.
the random work, but you can do this simultaneously for a lot of targets.
Yeah, it's like, so we have a big graph. So a big graph is here. So if we apply the graph convolution network, we need to use this whole graph as the input, and we need to run it simultaneously. But now, so what we do in this method is each time he just collect the information of oneself and its neighborhood. So he just get a cut of the original network as the input, and so this cut will be the new samples. Be the new samples of neural network. So the samples, when you train the neural network, is a lot of small subgraph of the original graph. So then you can use a lot of like a parallel way to do the stochastic gradient descent. Yeah, instead of directly use the whole graph. And also, if now you have a new cells into the original network, so you also gather itself and its neighborhood, yeah, as a sample, so you can find the results of it. And also when we construct I think the key point why he can do this is when he constructs this small subgraph, he do not use the original graph. Yeah, he used the graph he sampled by random walk. Yeah, so you can see that. So different cells, for example, so here we have A cells, but here we can also have a D cell. So D cell and his neighborhood can have five five cells in total. But here we only have 3 cells in total. So since these two different networks have different structures, so it's hard for you to trace them as a same input to a model. But now, so by this random walk procedure, so for each cell, so you sample the same number of neighborhood. So for A, we sample 3B and 2C. So we sample the so this is the new network we want to input in the model. And maybe for D, we also build 5 network by random walk, and he can also sample 5 cells here. So these two structures are the same, so you can trace them as the same input into a model. And even for a new cell, you do not a new cell. The new cell is not used when you train the model. So you can also do the neural network to sample maybe 5 neighborhoods and get the same structure, yeah, of the other subgraph, and then as the input as an input of the model. And here I only introduced the one-step random walk. So you can also do the two-step random walk. So after you sample B, so you can sample the neighborhood of B. For example, to B you can sample to E. You can from C you can to the other thing. But the things you need to determine is how many neighborhood you want to sample, how many random walk you want to sample. So here, so usually, for example, here we determined the number of first step neighborhood is 5. You can also determine maybe we want to sample 10 second step neighborhood. And after that, so the things you will get is A as the center. And it's the first step neighborhood, we have 5. And the second step neighborhood, we have 10. So in this inductive learning, so he aggregate all the information of cell A itself and the 5 first step neighborhood and the 10 second step neighborhoods together to generate a new feature vector. So X combined with the first X of A of its first neighborhood. So I is maybe A's first neighborhood or second neighborhood. And he aggregates them maybe by a kind of function to get the final feature of A. And now, so this one can be the input of a one layer neural network. So now the input of this one layer neural network is not XA, but XA star. This is the one aggregates all the information of its neighborhood. So you can see that by using the random walk, so you do not need to using the whole graph, and you do not even care about so how the true neighborhood of how the true neighborhoods of a cell. You only use the random walk to generate like to generate to generate the information of neighborhood. So you can treat as that. So we use 5 node to represent all the information of its first step neighborhood, and then we use 10 cells to represent all the information of the second step neighborhoods. So he do not care about which one he truly connected. He care about what kind of information in his neighborhoods. So that's the key point of this method.
Yes. So from here, I think the advantage of this is you don't worry how big the network is. So yeah, even it's a Facebook network, the whole global network, you'll still be able to manage to use a limited resource of the computation to approximate the landscape of this genetic network.
Yeah. This is also a way to to aggregate the information of a point and its neighborhoods. But in this way, you can cut the whole network into small samples, but
piece.
also include the information of its neighborhoods.
Yeah.
So the graph attention network and this one, so graph sage, both of them are some improvement on the tradition on the original graph convolutional network, and the people usually so combine these two ideas together, to build a model.
Hi, yeah. I have a question. So the weight matrices for in the graph sage, is it identical for those smaller circles that you draw, or they are different? It's like
You mean which one? Which
the small circles you draw within the big graph is right here, the left hand side. Is the weight matrices are all identical for those small circles, or
so here you can still include the self-attention idea. So in this paper, so this is the earliest paper. So he just set the same weight. So the so this is the aggregate. So how you define so this aggregate function. So just like the original graph convolutional network, you can use the same weight to all of these cells. Just to do the average of them. So you can also use other way. So actually, so in the paper, so he introduced several ways to design this aggregate function. One way is just to take the average of them. So this is one way, but there are other ways. But all of these ways are designed or pre-selected by people. But you can include the idea of self-attention. So to design the weight of each neighborhood. So yeah.
So in the original paper.
So that is also just one sentence. So that is why I say you can combine the idea of this graph stage and the self-attention together.
Yeah, I think the intuitive understanding why the graph set consider the sampling is because they wanted to have a neighborhood function with a constant number of cells. Is that right?
Yeah.
Because you have the constant cells, then you have the more general structure of a neural network, and the weight matrices for those small circles would be generalized.
To make the number of cells used in the first in the first step neighborhoods. Yeah, I think so. So list 5 and 10. So just I decide 5 and 10. So in the paper, so there are two important parameters you need to determine is the number the number of a first step neighborhood you want to sample. And we can go to the paper. Okay, so here you can see that he just want to sample the neighborhood. So in this paper, so he said it is enough for us to sample the two-step neighborhoods. So he also tried k equal to 3 or equal to 4. So they are the third step. They are the three-step neighborhoods, but I think that is too far away and do not make much contribution to the model. So he just used k equal to 1 equal to 2.
Okay.
Hi. Can you hear me? Can you hear me?
Yes.
Okay. So, I think my computer.
Yeah, we still can hear you from your iPad.
Okay.
Yeah.
So for the next step, you need to determine after the sampling, he aggregate all the features from its neighborhoods to the center point. Yeah, so that is the key point. Okay, my computer is
It's run out of the
out
battery.
of work. Yeah.
Yeah.
I do not notice it. Okay. Come back.
Okay.
Okay, just 1 minute. I will come in again.
Recording in progress.
Okay.
Yeah, I think this just provide a new way to sample from an extremely large network.
Yeah. Actually, random walk is not a new method, but it provides a new way to deal with maybe the problem if your input is very large and your input include a connection between different cells. And here is the key algorithm. So it's very easy. So you can see the input. So the input. So this weight matrix. We will learn it, but now if they are known, so we can use them to calculate the output of each layer. And here, so we need to. So here, so at the beginning, so we have for each layer, so we have the features of a cell U itself. So it is denoted as HUK minus 1. So this is the input of the K minus 1 layer. And now we want to gather all the neighborhoods of it. So here, if V is the cell we focus on, and then we want to aggregate the neighborhoods information of all HUK minus 1 to get a new features which to represent the neighborhood information. Yeah, I think so. And here, so he combined so the original feature and the new feature we get as the input of a neural network. Yeah, to do this is just a one layer neural network. So you can see it do the linear transformation first, and then do the nonlinear transformation. So for this is what the graph sage do in each step. Just before each layer, he generates he generates a neighborhood feature. Yeah.
So each time it's only update vector representations around the target cell.
He do not need to update. So the parameter, so in this model, it's only W. but each time the input can be only one self. So here, we can make this model easier. So first we can treat k only equal to 1. So we only have one layer. So we can ignore this loop. So here our loop is here. So for each node we have, so we can treat each node as a sample. We put it into this model. So the first step is from this cell. So we sample, we use the random walk to sample his neighborhood and then gathered just one vector. So this one vector, which contain all the neighborhood information of the target cell. And then combine with the information itself, we take them as the input of a one layer neural network. Yeah. So yeah. So the key point is he just include this step. Okay, and there are several ways to design this aggregate function. So
yeah, can you repeat the algorithm? I have a question. So does the order of the neighbor nodes matter? Because here you just have one W, right? If you just consider the depth equal to 1, step 1 neighbors, and then you sample.
No. This is not a step 1 neighbors. So this aggregate already aggregate both the step 1 and the step 2 neighbors.
Oh, okay. Oh, got it.
Okay.
Yeah, maybe you can use more like max pooling or something to.
Oh yeah.
The features of it.
For example, yeah, the max pooling is so the mean aggregator is what I said. So he put the same weight for all the neighborhood he sampled, and you can see here is max pooling. So he used the max pooling to yeah, just what you say. And you, as I said, we can also include the self-attention idea into this point to build the aggregate function. But after you use the aggregate function to generate a neighborhood feature, so the next thing is just a one layer neural network. So all the things are included. All the things are included in this point, in this step. Yeah, and actually, so these two steps are very similar to original graph convolution network. So even the same notation, but the only difference is in this graph stage, the aggregate is based on graph sampling. But in the original graph convolutional network, so we use the adjacency matrix to do this aggregate. Okay. Any questions? Okay, so I think that's all I prepare.
Yan, can I ask you a question?
Oh, sure. Yeah.
So you mentioned that all the nodes are samples, right?
Yeah.
So what's the reason you don't use feature as nodes?
Is your question that why he do not use all the neighborhoods?
Yeah.
But just the neighborhood he samples. I think he want to make a balance. So he treat more about what is the information of his neighborhood, but not what is but how many neighborhood he has. Yeah. You can simply sample like we just use 5 samples to represent all its neighborhoods. Yeah, we do not want to we do not want to take the average of all its neighborhoods. We just use random sampling, yeah, to sample 5 neighborhoods. So the good point is, if we use this sampling strategy, then for a new for a new age for a new cell, we can also sample 5. So since we can also sample 5, we do not need to sample all of his neighborhoods. So I think this is he what he want to get is the information of his neighborhoods, but not what is his neighborhood. Yeah, something
So
like that.
sorry, I think sorry, I think I
Yeah, you can look at this graph. So if in the original, I mean, if we use the original graph convolutional network, then we need to aggregate so all the points, so in this big circle.
yeah, I
So
mean,
because all of them are his 2-step.
my question is that can you replace the, I mean, each node in this graph cells, right? But
Yeah.
why if we just use strings as nodes?
Oh, I think the first problem is the graph is assumed to be known for us. Yeah, so we do not construct a graph. We know the relationship of cells. So for our context, for the single cell context, so for example, we can do to Tisney or some other dimensional reduction method. Yeah, maybe we can construct the KNN the KNN graph of cells. So that is easy. So it is easy, yeah. But I think it is hard for us to directly find the graph of genes. Yeah.
So if we can find a way to find this graph.
I think the thing I want to do is just I think our goal is to learn this graph. Yeah, it's like to learn the network of genes instead of just using the network of genes. But if we can have some high quality information of gene network, we can also try to use this kind of thing to maybe for other application. But now, so for most of applications, so the correlation between samples, so between cells, are more easier and available for researchers to get.
I see.
So yeah, and actually this graph convolution network is an extension of the convolution network, the CNN convolutional neural network. So convolutional neural network has already been studied for a long time and applied to a graph, to photos. So so in the in that convolutional neural network, since the pixels of each figures are highly correlated, so we can also use that kind of link, just like the neighborhood of cells, to help improve the model. So yeah, so I think it's okay to include the information of genes, but the thing is, I don't know if we have that good information. Or another way is maybe we can use self-attention to try to learn the relationship between genes, but I'm not sure if that result is meaningful. But that's a good point. Yeah.
If we use like PCNet to learn this kind of graph, is that possible to to do this?
I think it depends on what you want to do. So for most of this method, so the thing we want to do is for each cell, we generate a low dimensional features for it. But low dimensional like representation, and then we use this low dimensional representation to do other things like classification or something else. But if you treat like each one as a gene, so your output, I'm not sure. So what kind of output you want to do? do.
Okay, thank you.
I want to mention something unrelated to this, and just if you look at this number 3 panel here, of course, in this application, try after learn this, you want to have some inference about the graph and some label. What I'm thinking about is something else. So if we treat each node here is a cell, so you have a network between cells, like a KNN network between cells relationship. In this case, each cell is represented by its gene expression profile, which is a vector.
Yeah.
Remember, we can build gene-gene interaction network. So we can convert this gene expression profile vector for each individual cell, make it into a gene-gene interaction network. So if we do that, every cell on this cell-to-cell network is defined by a cell with each cell contains its gene-gene interaction network. Of course, the backbone of this gene-gene interaction network will be the same across all the cells. However, we can change certain parameters for make each cell's gene-gene interaction network unique. So that will create a new data structure. So you have a cell-cell interaction network. Each cell is presented by gene-gene interaction network. So it's network's network.
Oh, so
I don't know if anyone has ever done those.
So you mean that for each cell we can maybe use some existing method to have a gene regulatory network for each cell.
Yes.
So I think this is what also I'm doing. Yeah.
We call the single sample network.
Yeah. But for I just want to mention a process of network. So for network, I transformed the single cell network. I mean, the unicellular network to like cell groups. So I detected the subgroups of cells and build the neural network. Build the graph network. Build
for genes.
the network for genes. Yeah, because I find that. For each cell, it is too noisy.
We can use a supercell. So you have a supercell here.
So I just use a subgroup of cells to build. I try to find the subgroup of cells that has unique gene regulatory network. And also so both what Dr. Tsai and you mentioned. I think what I'm also want to do. Yeah, that's why I read this kind of method. I want to use this graph-based neural network to maybe construct cellular gene regulatory network, or maybe find a better way to construct the gene regulatory network, because I think currently there are only a little work on how to use the neural network to construct the gene network. So maybe
Yeah.
yeah, the current the existing method are not much, and maybe only 2 or 3, and their work may not be that reasonable. Yeah, yeah.
Yeah. Okay, I think that's
Yeah, I have
something new.
can I still have a
yeah.
question? It's for this graph stage, what's the loss function? Is you want to reconstruct your future matrix or your adjacent matrix?
Yeah. So for this paper, so he considered both of them. So first, if you want to do like a dimensional reduction method, so the things is you want to recover your then you want to recover your adjacency matrix. So this is the I think this is the let me see. This is the unsupervised study of it, I think. So learning the, yeah, here. So this is the unsupervised setting. So in the unsupervised setting, he want to recover the original GC matrix. Yeah, so he built this loss function. So for the if two nodes are similar to each other or they are connected in the graph, so he wanted the final low dimensional features. So ZU and ZV for a pair of node U and V, they should also have a larger have a large value compared to other things. So this one is a loss function related to the probability, yeah, of that. And also if you're if you want to do like the node classification, so for some supervised settings, so if you have the label of cells, so you can use this Z, maybe build a linear build a logistic model or some classification loss function. So that is a loss function. So this is a loss function. So Z, so what Z here is the output of 2 layers. So here, so in first step, you aggregate the neighborhood information. In the second step, you put it into a one linear neural network, and the output is just Z here. Okay.
Yeah, I was just curious about if we objective of this algorithm is to reconstruct the original X. What's is the lower dimensional representation Z has any meaning?
You mean if we want to construct the network, right?
Yeah. I think it doesn't make sense, right? It's
yeah. So I think if we want to do it, we cannot directly put it into the neural network, because neural network will transform your original like gene features. Like you will transform the gene features, but we want to keep some can keep the neural these gene features and find the relationship between them.
Thanks.
Yeah, you need to use maybe other way to take them as the input and output. Okay. Okay, so let's all.
Okay, good. So, Yunjian, are you going to still very quickly go through the paper you discussed?
Yeah. So
in 15 minutes, because I have to leave. Yes, about 15 minutes.
Oh, okay.
Yeah.
So it's about we had a collaboration with Dr. Neto's lab, and they're focusing on the physical informed neural network. So what's just a little bit background about what's the physical informed neural network. So suppose you have a PDE here, and I mean, their intention is to just use the neural network to feed forward the traditional neural network to solve the PDE equation to get the solution of this PDE partial differential equation mu. So we define a neural network equals to the residual of this neural network. So here we just move the 0 to the left-hand side and we get the residual. So the loss function is like this. Suppose we have we have a bunch of data, but not a lot. So we still have our MSE loss, the mean square error. So it's just like this. L2 is the L2 distance, the arrow. And another term is the MSE with respect to this governing equation, the physical informed PDE. So we want our residual F, which is a neural network parallelized by some parameter theta, to be as small as possible. So ideally, we want this term to be 0, which means all the samples, all the data that we got, they will follow this physical PDE. Right. So that's the basic idea of the physical informed neural network. So about their application in the world of biology, I found this paper is quite interesting. Is they use the recurrent neural network to build the gene regulatory network. So here is the main idea. You can see it. So so first of all, the data they collected are time series data. So the governing equation, the governing PDEs look like this. So it's suppose for the simplest model, suppose you just have 2 genes and 1 signal I. So signal I could be any stimulus or any repressor signal for the which work on the gene expression. So your gene would change like this across time. So this is a typical, I would say ODE. Yeah, it's the ordinary differential equation. But here the F is unknown, and here the author defined this F as a neural network. So the F is a neural network with some parameter theta, and their input would be G1, G2, and I. So that's the main idea. And as you can see here is the first order derivative of G with respect to the time t. So the idea is like this: you rewrite this PDE ODE like this. The dt, the next time point minus the current time point would be your derivative. So that's you just discretize your ODE function to look like this. So if you look at this, we just move this GT to the right hand side, and it can be modeled by a recurrent neural network, because the next stage of gene expression would be the function of some input from the previous stage and some neural network F. So your input would be the G with the time t, and the I. I is the signal. Could be any biology stimulus with respect to time t. And the output would be this neural network. The output would be the F, F1 and F2. It's just this F, this F. So this F could be interpreted like the synthesis expression of gene 1 and gene 2. So suppose you have gene 1 here, gene 2 here, and this node is the signal I, and you will compute the F1 and the F2 values at the time equals to t, some t. Right after you get the value of this F1 and F2, you introduce them to this equation, and then you will get the output of GT plus some DT. So does it make sense? I think the input is G1, G2, and I at some time t, and you will output the F1 value F1 at the time t and F2 at the time t, and you introduce this F to the equation here, then you get the gene expression of a next time point. So it's a supervised learning because we have the time series data. So we can train this recurrent neural network. And after they train, the figure C shows some result. For example, the function F is a function of F, as you can see from this model, is a function of G1, G2, and I. And here we just let's feed some variable, and we got the curve of F, how the F change across I. And you can see as I increase, the F also increase. So the infer the gene regulatory network is that I will positively stimulate the gene 1 and gene 2. And the same logic apply to these two curves. For example, if we feed I and G2, and we see the F1 and F2, they both increase when the G1 increase, which means the G1 will positively govern the expression of G2. And also self-govern. I cannot draw. Also self-govern itself, the G1 to the G1 itself. So that's the main ideal that they infer from the result, how they obtain a gene regulatory network from the F. F is the synthesis curve with respect to the gene 1 and gene 2 expression level. So after we get that, how we use this recurrent neural network, I think we can do some simulation. For example, if we change the value of this IT, the gene expression of gene 1 and gene 2 the curve will change, and we will see how they change according to different type of signals. For example, figure B shows there is a step signal I. If you set your I like this, and you will get your the curve of gene expression G1 and G2 change across time like this. So that's the main idea of figure 1. And another interesting part is like, they also did some simulation of perturbation. For example, in the figure A, in the figure 2A, they want to simulate the result after you knock out gene 1. So you knock out this edge from gene 1 to gene 2. So it's a directional edge. So the idea is the same as figure 1 shows. So after we train a recurrent neural network, we divided them into two, and we just said the second recurrent neural network G1 value equals to 0. So which means this F2, the output F2. So the F2 stands for how the gene 2 expression level change across time. And you said the gene 1 value here is 0. So which means the F2 output would be the simulated result that you knock out gene 1. So that's a result they got. There is a figure B. After you knock out this, it shows how the curve change. It's like originally you have this dark you have this dark green, the gene 2, and after knockout the gene 1 to gene 2, your expression level increased a little bit. So which means they infer that, which means G2 might out regulate itself to increase their expression level. So that's basically all the idea, and they have some details, but time is limited. So do you have any questions with respect to this?
Yeah.
Go ahead.
Oh yeah, I have a question about so how is the data? Yeah, or yeah, how you I mean how is the data? So you say the data is time series data. So
yes.
Yeah, but how can we get this time? So
I think they have some benchmark biology data, but when I searched their GitHub, they didn't provide the raw data, so I'm still fighting it. But basically, it's just the gene expression matrix change according to time.
Okay, I think that is very I mean the very important like data set.
Yes,
I mean
yes.
if they truly have it, because I think it's very difficult to get this kind of data. Yeah, just
so
yeah,
it's possible for a small number of genes. So they use fluorescent the light to indicate the expression level. Then they have a microscope to continuously record this signal density across time within the dark room. Okay, if you can see, okay, this green light become stronger along the time, and this pink light become weaker, so you can have a continuous measurement every seconds, maybe over several hours. So it's possible to get this information in the controlled petri dish experiment. But it's not a single cell level. It should be aggregate a subpopulation of cells.
Oh, I'm thinking maybe we can use the pseudo time to pseudo time single cell.
Yeah, so we certainly can use pseudo time and imputation to make it a continuous variable and normalize it.
But just another thing that I think when we use pseudo time, we may need multiple pseudo time. I mean, I think like how to compare the time for because we need some training data set. Yeah, so I think for this kind of study we need several data set, and they are comparable. So that's why I think this data set can be very interesting and important.
Yeah, so we can have a single cell sample collected from real time, different time points, day 1, day 2, day 3. And for each date, for example, cells in day 1, we still make this pseudo time, then the cell will overlap with pseudo time in the day 2 as well. So you have a really long continuous variable, some genes change along the time. And it's possible nowadays. It's possible. But on this example, we can treat I as another gene, right? You have a gene 1, gene 2 and I is gene 3.
Yeah.
You don't have to have a perturbation in there. Okay, that's good. So Christine, do you have any questions for this you had?
Yeah, this second image, the second picture is for testing. Doesn't include any training, right?
You mean the figure A?
Yeah, the figure A.
Yeah, seeing the preconditions, you already train your recurrent neural network, and then you manually set the gene 1 expression as 0 in the second.
Yeah, so both networks are the same, just the input in the blue one just is set to 0.
Yes,
okay.
Yeah, you're right.
But the output of this figure, it was have both blue and the green genes output, but in this graph, the only output blue gene. So if you compare this one against the figure 1, you have 2 genes expression.
I think figure 1 is just you can see the second like this. This is the figure 1. They just use one RN to compute F1 and F2, but now we use 2 to compute F1 and F2 because this is directional, the gene network.
Okay, doesn't matter.
So that's all my presentation.
Yes, okay. So just replace the neural network to solve this. So you don't have any analytical solution and you don't know the parameters, but just rely on the neural network to generate the output. Okay. All right, anything else? No? Okay. So I recorded this. If Guanxiu need to review this, he should be able to. Otherwise, we will gather again in 2 weeks. Oh, I don't know whether in 2 weeks it will be holiday. Oh, maybe we have to skip 1 week, 1 meeting, or we shift to January 6th next year. So we will have a gap 2 weeks and then come back. Chen will email us, okay?
Yeah, no problem.
Okay.
Yeah. Everyone have a good Christmas in Taiwan and Shanghai.
Thank you.
Okay.
Thank you.
Yeah. In the meantime, we email each other and about the manuscripts and also the final version of KNK and the interaction single cell 24 interaction will be released very soon. Okay, good. Bye.
See you next time.
See you. Bye, Yuda.